Okay, welcome back to our AI course series. I'm Dr. Shan Shi, and in this lesson, we are going to take another important step forward. If you look at the title on this slide, today's focus is opening the black box. In the previous lessons, we discussed what AI is, how it is defined, and how it can be classified. But now, we move to a deeper question: how does AI actually work? So today's lesson is not about advanced mathematics. Instead, it is about understanding the core logic behind modern AI in a clear and intuitive way. Let's begin with today's objective. This slide states the goal very clearly. We want to understand the core logic of machine learning without complex mathematics. That is important, especially for business and management students. You do not need to become an AI engineer, but you do need to understand the underlying logic well enough to ask smart questions, evaluate applications, and make better strategic decisions. So the goal of this lesson is conceptual clarity, not mathematical mastery. This is our roadmap for today. If you read down the slide, you can see 4 major parts. We begin with the shift from rules to learning because that is the foundational revolution behind modern AI. Then we move into the 3 pillars of machine learning, which are supervised, unsupervised, and reinforcement learning. After that, we introduce deep learning, which is one of the major engines behind today's AI boom. Finally, we close with summary and discussion. So today's lesson is really about one big transformation from humans writing rules to machines learning rules from data. Now let's open the black box. If you look at the 2 images on this slide, they immediately create a contrast. On the left, we see a human working through formulas on a blackboard. On the right, we see a robot reading and learning from information or knowledge. This visual contrast is very effective because it captures the transition from traditional programming to machine learning. The left side suggests that intelligence comes from human-designed rules. The right side suggests that intelligence comes from data, examples, and learning. That contrast sets up the entire lesson. So let's start with the older model, Software 1.0. The slide emphasizes rule-based and symbolic logic. And you can also see the repeated phrase, if then. That phrase is the essence of traditional programming. If the old paradigm, the logic is simple. Human analyze the problem, define the rules, and then write those rules into code. So the machine does not learn the solution. It merely executes the instructions we have already decided. This works very well when the word is structured and the logic is clear. For example, payroll calculation, tax rules, or a highly controlled business workflow can all be translated into explicit rules. However, we have some limitation of rule-based thinking. Please look at the images along the bottom of the slide. We see different kinds of cats, but also a tiger and a fox. This is a great visual example because it forces us to ask, what exactly rule defines a cat? Does a cat have pointed ears? Then what about a folded ear cat? Does a cat have a fur or a tail? Then what about a fox? Does a cat have a certain face shape? Then what about a tiger? This is exactly the problem. Humans can usually recognize a cat instantly, but we cannot always translate that recognition into a complete and reliable set of explicit rules. This is what makes real-world perception hard for traditional programming. This slide shows the fundamental reversal that created modern AI. If you look at the slide, the visual is arranged as input, process, and output. On the left, we see many examples of cat. In the middle, we see a machine learning system. On the right, we see the result. The system outputs the label cat. This is the core idea of Software 2.0. In traditional programming, humans write the rules. In machine learning, we provide data and examples, and the machine discovers the rules for itself. That is why the keywords at the bottom matter. Data-driven, backpropagation, self-improvement. The system becomes better not because a programmer rewrites every rule by hand, but because the model adjusts itself based on data and error correction. So now let's connect machine learning to a broader definition of modern AI. This slide uses a circle diagram, predict, action, feedback, improve. That circular structure is very important because it shows that AI is not just a one-time calculation. It is a system that can improve over time through repeated interaction and data feedback. This is why the phrase AI factor cycle is so useful. In modern business, AI often operates as a loop. It makes predictions. Those predictions affect actions. Those actions generate outcomes, and those outcomes produce feedback that helps improve the model. So the real power of AI contemporary is not only automation. It is continuous learning and performance improvement. So we move from the general idea of learning to the three major ways machine learning. These slides use a very memorable visual, three column supporting the rule of modern AI applications. This image works beautifully because it tells us that these three learning paradigms are the structural pillar of machine learning. So the three pillars are supervised learning, unsupervised learning, and reinforcement learning. So when you see this slide, think of it as the architecture of machine learning. Different business problems call for different pillars. So let's begin with the first paradigm, supervised learning. And this is the most common and commercially valuable paradigm. This image on this slide is very intuitive. We see a teacher holding up a cat card and a dog card in front of students. That is an excellent metaphor. Supervised learning works like learning with answer keys. The model is shown example together with the correct answers. That is why the key words at the bottom are labeled data and mapping into outcome. You give the system input such as customer characteristics, house features, and or medical images. And you also give it the correct output, such as churn or not churn, house price, or diagnosis. The machine then learns the relationship between the two. So if the question is what will happen or which class does it belong to. Supervised learning is often the right tool. Then let's move to the second pillar, unsupervised learning. The image here is very helpful. We see a child sorting a pile of mixed blocks into groups. That visual is exactly the logic of unsupervised learning. No one gave the child the correct labels in advance. Instead, the child discovers structure by grouping similar objects together. That is why the key words are unlabeled data. Clustering, association. In this paradigm, the machine is not being told what the correct answer is. It is being asked to explore the data and detect patterns, segments, or relationships that were not obvious before. In business, this is especially useful for customer segmentation, anomaly detection, and market structure discovery. Now, we come to the most action-oriented learning paradigm, reinforcement learning. The slide used two excellent examples. On the left, we see dog training. On the right, we see a child learning to ride a bicycle. Both examples involve trial and error, feedback, and gradual improvement through reward and penalty. That is exactly how reinforcement learning works. The system is placed in an environment, takes action, observes consequence, and gradually learns which action lead to better long-term rewards. So this paradigm is especially useful for sequential decision-making situations where the next move affects further possibilities. That is why reinforcement learning is important in areas such as game playing, robotics, route planning, and dynamic pricing. So this one is a useful summary slide because it organized the three learning paradigms into a decision table. So please see the table and go row by row. For supervised learning, emphasize precision and labeled data. For unsupervised learning, emphasize exploration and unlabeled data. For reinforcement learning, emphasize decision-making, interaction, and feedback. So this slide is essentially answering one practical managerial question: what kind of learning problem do I actually have? Once you know that, you are already in a much better position to choose the right AI approach. So now, we move into the final major part of the lesson, deep learning. This slide is very visually clear. On the left, we see biological neuron. On the right, we see an artificial neural network with input, hidden, and output layers. That side-by-side comparison immediately tells us the main idea. Deep learning is inspired by the structure of the human brain. But the most important teaching point here is this. Deep learning is not a completely separate idea from machine learning. It is one of the most powerful technical architectures within machine learning. So when students you hear the term deep learning, you should think multi-layer neural networks. They are especially powerful for complex perception tasks. This is one of the most important visuals in the entire lesson. If you look at the image, you can see 3 layers, 1, 2, 3. At the bottom, the system detects the simple visual fragments, such as edges and textures. In the middle layer, those fragments become parts, such as eyes, nose, and ears. At the top layer, those parts become full face. This is what hierarchical representation means. Deep learning is powerful because it learns in layers, gradually transforming raw data into increasingly meaningful abstractions. So instead of telling the machine, this is what an eye looks like, the network discovers those intermediate features for itself. So let's use this slide to help us understand why deep learning changed the world. On the left, we see a spreadsheet that represents structured data. The kind of data traditional AI and classical machine learning were already relatively good at handling. On the right, we see an image and audio waveform representing unstructured data such as picture, sound, and speech. This contrast is the real breakthrough story. Deep learning became transformative because it gave the machine much stronger ability to process data that did not fit neatly into rows and columns. So when people ask why AI suddenly became so powerful in the 2010s? One key answer is deep learning became much better at seeing, hearing, and eventually reading. So this slide summarizes the business value of deep learning in a very sensory way. If you look at the images, we can see an eye, an ear, and a mouth. Those three visuals symbolize perception, vision, hearing, and the language or speech. That is exactly the business significance of deep learning. It gives machines stronger perception capabilities. And the keywords at the bottom: automated feature extraction and high-dimensional data capture the technical meaning behind that business value. Deep learning can automatically discover relevant features in very large, complex data spaces, especially when humans cannot easily specify those features in advance. So let's see the excellent final architecture slides because it brings the whole lesson together. If you look at structure, it is designed like a multi-layer building, right? At the top, we see the core principle of software 2.0, moving from rules written by humans to rules learned from data. In the middle, we see the three learning paradigms: supervised, unsupervised, and reinforcement learning. Below that, we see deep learning as the engine, and at the foundation, we see big data, which acts as the fuel. This is a very good visual summarize because it shows that modern AI is not just one thing. It is an ecosystem made of principles, learning paradigms, computational engines, and data infrastructures. So when you finish the lesson, I want you to remember this image as the skeleton of modern AI. So that brings us to the end of lesson 3. Today, we opened the black box just enough to understand the key transformation behind modern AI. We moved from rules written by humans to rules learned from data. We also saw the 3 major learning paradigms and why deep learning became so powerful in handling unstructured data. In the next lesson, we will continue by connecting this algorithm idea to business systems and organizational value. In other words, once we understand how the engine works, the next question becomes, how do companies actually build value on top of it?